Well, welcome back to College Physics 3. We're continuing our journey in the second part of this course, the second semester. And so far, we have covered several topics in electricity and magnetism. We talked about electric forces and fields. Then we started to talk about specific components that are used in electrical circuits, capacitors and resistors. We introduced the idea of current. And in this lecture, we're going to be now talking about a kind of current, something called direct current or DC. And in several chapters, we'll be talking about alternating current or AC. But for now, we'll focus on topic number 18 and looking at direct current circuits. And so first, before we get into some of the details here, we'll go ahead and do a quick review over the reading questions. This information is in the lecture notes, and it's based on the material in the textbook, so I won't spend too much time going over this, but quickly read them. You could pause and think about these as you go. So the first one, in order to calculate the fraction of the total power delivered to the load resistor in a circuit consisting of a battery and a local resistor, one needs to know only, and the answer is the load resistance and the internal resistance. We'll get into that in a little bit more detail here. Battery placed in circuits with different load resistances can be considered as a source of constant, and the answer is EMF. As more resistors are added in series, the equivalent resistance of the circuit approaches infinity. In contrast, as more resistors are added in parallel, the equivalent resistance approaches, the answer is 0. You'll notice it's a complement to what a capacitor is. At the moment the switch closes on this freshly connected RC, resistor capacitor circuit, what happens? And the answer is Q equals 0 and I equals epsilon over R. Epsilon is the voltage of the battery. So V equals IR is that equation for the second part there. As the capacitor in the RC circuit reaches its maximum charge, so we have a diagram here with the switch closed, a capacitor and resistor. The answer is both rates decrease. Kirchhoff's loop rule is equivalent to which of the following principles? And the answer to this one is conservation of energy. And that's something we've covered before. And so now we'll get a chance to explore how that looks in circuits. Appliances with 3-prong plugs compared to those with 2-prong plugs are conservation of charge and safer to use and connected to ground. And that's one key feature for that. So you can keep that in mind. So now we'll get into the discussions here. And so this is an area where we deal with a lot. We rely on circuits for all kinds of modern conveniences, such as electrical lights, electrical stove tops and ovens, washing machines, and lots of other appliances and tools. Electric circuits are found in our cars and all types of medical equipment. And for this topic, we will analyze simple direct current circuits, which include resistors or capacitors or both. Our analysis will be simplified by using 2 rules known as Kirchhoff rules, which follow from the principle of conservation of energy and the law of conservation of charge. Most of the circuits are assumed to be in steady state, which means that the currents are constant in magnitude and direction. For the circuits containing capacitors, the current will vary with time. So we have this figure on the left. It's a circuit consisting of a resistor connected to the terminals of a battery. And on the right, we have a circuit diagram of a source of EMF epsilon having internal resistance R and connected to an external resistor R. So if we take a look at the figure on the left, the battery is a source of EMF and it maintains the current in the circuit. An EMF source is any device such as a battery or generator that increases the potential energy of the circulating charge. We can think of an EMF source as a charge pump that forces electrons to move in a direction opposite the electrostatic field inside the source. The EMF of a source is the work done per unit charge. So the SI units of the EMF is the volt. And so basically you're seeing that there's a voltage here across the battery. And so that's where you can be thinking of it as EMF, but just thinking this is a voltage source, a battery or some type of power source. So let's think of this question, true or false. While discharging, the terminal voltage of a battery can never be greater than the EMF of the battery. And the answer is true. When a battery is delivering a current, there is a voltage drop within the battery due to the internal resistance, making the terminal voltage less than the EMF. So what does a battery get warm while in use? Why does a battery get warm when it's in use? Something to be thinking about. And the answer is because of internal resistance, power is delivered to the battery material, raising its temperature. Because of internal resistance, power is dissipated through the battery material, raising its temperature. This is the rationale behind that. Let's think about resistors in series, which is the opposite of how it would be if you have capacitors in series. And so in the figure, we have resistors R1 and R2 in the form of an incandescent light bulb in series with a battery. The currents in the resistors are the same. When two or more resistors are connected end to end, as in the figure on the left, we say that they are in series. Resistors could be simple devices, for example, light bulbs or heating elements. When two resistors R1 and R2 are connected to the battery, the current is the same in the two resistors because any charge that flows through R1 must also flow through R2. This is analogous to a water flowing through a pipe with two constrictors corresponding to R1 and R2. Whatever volume of water flows in one end flows in one end in a given time interval must exit the opposite end. Because the potential difference between A and B in the middle figure equals IR1, and the potential difference between B and C equals IR2, the potential difference between A and C is given by the equation that we're showing. It doesn't matter how many resistors we have in series. The sum of the potential differences across the resistors is equal to the total potential across the combination. The result is the consequence of the conservation of energy. So let's continue this. So in the figure, we have the equivalent resistance of the combination is R equivalent equals to R1 plus R2. And so we can see if we wanted to simplify that schematic, we're seeing that over here on the right. So the circuit on the left can be drawn with an equivalent resistor EQ that can replace the two resistors of the original circuit as shown in the right. The equivalent resistor has the same effect on the circuit because it results in the same current in the circuit as the two resistors. So let's apply Ohm's law to the equivalent resistor. We can extend our analysis for more resistors in series. This equation tells us that the equivalent resistance of a series combination of resistors is the algebraic sum of the individual resistors and is always greater than any individual resistance. Note that if the filament of one light bulb in our circuit represented by resistors here were to fail, the circuit would no longer be complete, and the second bulb would also go out. So you can think of a Christmas tree lights. If it has a series way that they're hooked together, that's exactly what you'd see would happen. The whole string would go out. So in the figure below, the current is measured with the amp meter at the bottom of the circuit. When the switch is open, the reading on the amp meter, and the answer is decreases. So when the switch is open, resistors R1 and R2 are in series so that the total circuit resistance is larger than when the switch was closed. As a result, the current decreases. So basically, you've shorted out the resistor when you have the switch closed, and when it's When it's open, then you have both resistors. The circuit in the figure below consists of two resistors, a switch and an ammeter and a battery. When the switch is closed, power PC is delivered to the resistor R1. When the switch is open, which of the following statement is true about the power PO delivered to R1? And the answer is PO is less than PC. And the reason is when the switch is open, resistors R1 and R2 are in series, so the total circuit resistance is larger and the current through R1 is less with a switch open than when it is closed. So, okay, so we talked about resistors in series. Now let's talk about resistors in parallel. And so in the figure, we have two resistors, R1 and R2, in the form of incandescent light bulbs in parallel with a battery. Now let's consider the resistors connected in parallel as shown in the figure. In this case, the potential differences across resistors are the same because each is connected directly across the battery terminals. The currents are generally not the same. So continuing with this figure, the potential difference across R1 and R2 is the same. Currents in the resistors are the same, and the equivalent resistance of the combination is 1 over R equivalent is 1 over R1 plus 1 over R2. So looking at the figure on the left, which is a schematic of the circuit shown on the previous slide, when charges reach point A, called a junction, the current splits into two parts, I1 flowing through R1 and I2 flowing through R2. If I1 is R1 is greater than R2, then I1 is less than I2. In general, more charge travels through the path with less resistance. Because charge is conserved, the current I that enters point A must equal the total current I1 plus I2 leaving that point. The potential drop must be the same for the two resistors and must also equal the potential drop across the battery. So we can apply Ohm's law to each resistor. And when we do this, we can do the same thing with the equivalent resistor in the right-hand figure. If we substitute our results into the current equation and cancel delta V, then we get the following relationship. We can, as with the series case, extend our analysis to get the more general equation that we're showing on the bottom. From this expression, you can see that the inverse of the equivalent resistance of two or more resistors connected in parallel is the sum of the inverse of the individual resistances is always less than the smallest resistance in the group. So here's another question to think about. In the figure below, the current is measured with the ammeter on the right side of the circuit diagram. When the switch is closed, the reading on the ammeter, and the answer is increases. When the switch is closed, resistors R1 and R2 are in parallel, so the total circuit resistance is smaller than when the switch was open. As a result, the current increases. When the switch is open, as in the figure below, power PO is delivered to the resistor R1. When the switch is closed, which of the following is true about the power PC delivered to R1? And the answer is PC equals to PO. PC equals PO. Observe that the potential difference across R1 equals the terminal potential difference of the battery. If the battery has negligible internal resistance, the terminal potential difference is the same with the switch open or closed. Under these conditions, the power delivered to R1 equals to P equals to delta V squared over R. It's unchanged when the switch is closed. Here's another question. Suppose you have three identical light bulbs, some wire, and a battery. You connect one light bulb to the battery and take note of the brightness. You add a second light bulb connected in parallel with a previous light bulb. And again, take note of the brightness. Repeat the process with the third light bulb connected in parallel with the other two. As the light bulbs are added, the brightness of the light bulbs, and the answer here remains the same. So the voltage drop across each bulb connected in parallel with each other and across the battery equals the terminal potential difference of the battery. As more bulbs are added, the current supplied by the battery increases. For the same scenario in the previous slide, as the light bulbs are added, the individual currents in the light bulbs, and the answer is decreased. For a series connection, the individual currents in the bulbs are the same and equals to the total current supplied by the battery. This decreases as bulbs are added. Again, same scenario as the light bulbs are added, the power delivered by the battery, and the answer is decrease. The total power delivered by the battery is given by P total equals to delta V times I, where delta V is the terminal potential difference of the battery and I is the total current supplied by the batteries with a negligible internal resistance. Delta V is constant, thus when with I decreasing as bulbs are added, the total delivered power decreases. Once again, the same scenarios, the light bulbs are added, the lifetime of the battery, and the answer is increases. When the delivered power decreasing energy is drawn from the battery at a decreasing rate, which increases the lifetime of the battery. Continuing on, suppose you have three identical light bulbs, some wire and a battery. You connect one light bulb to the battery and take note of its brightness. Add a second light bulb in series with the previous light bulb, and again, take note of the brightness. Repeat the process with the third light bulb, connecting it once again in series with the other two. As the light bulbs are added, the brightness of the light bulbs, and the answer is decreased. And so we had a case with in parallel. Now we're talking about the cases when they're in series. Adding light bulbs in series with each other and the battery increases the total load resistance seen by the battery. This means that the current supplied by the battery decreases with each new bulb that is added. The brightness of a bulb is determined by the power delivered to the bulb, so that the power of the bulb equals I squared R, decreases as bulbs are added and the current decreases. So once again, with the same scenario, as the light bulbs are added, the individual currents to the light bulb, and the answer is decreases. For a series connection, the individual current and the bulbs are the same and equal to the total current supplied by the batteries. This decreases as bulbs are added. Same scenario again, and now we're talking about the power delivered by the battery, and the answer is the power delivered by the battery decreases. The total power delivered by the battery is given by P total equals to delta V times I, where delta V is the terminal potential difference of the battery and I is the total current supplied by the battery. With negligible internal resistance, delta V is constants. Thus, with I decreasing as bulbs are added, the total delivered power decreases. So for the same scenario, now we're talking about the lifetime of the battery, and in this case, the lifetime of the battery increases. With the delivered power decreasing, energy is drawn from the battery at a decreasing rate, which increases the lifetime of the battery. Okay, now we're talking again with resistors in parallel, and so household circuits are often wired so that electrical devices are connected in parallel. That means that each device operates independently so that if one is switched off, the other remains on. For example, if one of the light bulbs in the figure were removed from its socket, the other would continue to operate. Also, each device operates at the same voltage. If the devices were connected in series, the voltage across each one would depend on how many there were in the combination and on their individual resistance. In many household circuits, circuit breakers are used in series with other circuit elements for safety purposes. The circuit breaker is designed to switch off and open the circuit at some maximum value of current, typically 15 or 20 amps. That depends on the nature of the circuit. If a circuit breaker were not used, excessive currents caused by operating several devices simultaneously could result in very high wire temperatures and even cause a fire. In older homes, fuses were used in place of circuit breakers. When the current in a circuit exceeds some values, the conductor in a fuse melted and opened the circuit. The disadvantages of fuses is that they are destroyed in the process opening circuit, that circuit breakers can be reset. So let's talk about the problem-solving strategy for simplifying circuits with resistors. So number one, you want to combine all the resistors in series by summing the individual resistances and drawing a new simplified circuit diagram. You can use the equations for resistance in series, which are showing, and remember that the current in each resistor is the same. Number two, combine all resistors in parallel by summing the reciprocals of the resistances and then take the reciprocal of that result, drawing a new simplified circuit diagram. So you use the equation for resistors in parallel, which we're showing on this chart, and remember that the potential difference across each resistor is the same. Number three, repeat the first two steps as necessary until no further combinations can be made. If there is only a single battery in the circuit, the result will usually be a single equivalent resistor in series with the battery. Then you want to use Ohm's law to determine the current in the equivalent resistor. Then work backwards through the diagram, apply the useful facts listed in steps 1 or step 2 to find the currents in the other resistors. So here we'll talk about Kirchhoff's rules and complex DC circuits. And so as you have seen, we can analyze simple circuits using Ohm's law and the rules for series and parallel combination of resistors. There are many ways resistors can be connected so that the equivalent forms, the circuits formed can't be reduced to a single equivalent resistor. To analyze more complex circuits, we make use of two simple rules called Kirchhoff's rules. Number one, the sum of the circuit, the currents entering any junction must equal the sum of the currents leaving that junction. And then number two, the sum of the potential differences across all the elements around any closed circuit loop must be zero. The junction rule is a statement of conservation of charge. Whatever current enters a given point in a circuit must leave that point because the charge can't build up or disappear at any point. If we apply the rule to a junction in the figure on the left, we get the current equation shown. The figure on the right represents a mechanical analog of the circuit. In the analog, water flows through a branch pipe with no leaks. The water rate into the pipe equals the total flow rate out of the two branches. The loop rule is equivalent to the principle of conservation of energy. Any charge that moves around any closed loop in a circuit must gain as much energy as it loses. It gains energy as it's pumped through a source of EMF. Its energy may decrease in the form of a potential drop, the IR loss across a resistor, or as a result of flowing backward through a source of EMF from the positive to the negative terminal inside the battery. In this case, electrical energy is converted to chemical energy as the battery is discharged. So in this figure, we're showing the rules for determining the potential difference across a resistor and a battery, assuming the battery has no internal resistance. When applying Kirchhoff's rules, you must make two decisions at the beginning of the problem. Number one, assign symbols and directions to the current in all branches of the circuits. Don't worry about guessing the direction of a current correctly. The resulting answer will be negative, but its magnitude will be correct. Because the equations are linear in the circuits, all circuits are to the first power. When applying the loop rule, you must choose the directions for traversing the loop and be consistent in going either clockwise or counterclockwise. As you traverse the loop, record voltage drops and rises according to the rules shown in the figures. As you can see in the top left figure, if a resistor is traversing in the direction of the current, the charge in an electric potential across the resistor is minus IR. If a resistor is traversing in the direction opposite to the current, as in the top figure, the change in electric potential across the resistor is plus IR. If a source of EMF is traversed in the direction of EMF, from the minus to plus on the terminals, the change in electric potential is this plus epsilon. If a source of EMF is traversing to the direction opposite the EMF, the change in electric potential is minus 2 epsilon. To solve a particular circuit problem, you need as many independent equations as you have unknowns. So once again, the problem solving strategy, of course, the zero entry should be to read the problem carefully and then start forward with each of these. And so one, assign labels and symbols to all the knowns and unknown quantities, assign direction to the current in each part of the circuit. Although the assignment of the current direction is arbitrary, you must stick with your original choice throughout the problem as you apply Kirchhoff's rules. Number 3, apply the junction rule to any junction in the circuit. The rule may be applied as many times as a new circuit appears in the resulting equation. Number 4, apply Kirchhoff's loop rule to as many loops in the circuit as are needed to solve for the unknowns. To apply this rule, you must correctly identify the change in electric potential as you cross each element in traversing the closed loop. And so you want to make sure that you watch out for signs. Number 5, solve the equation simultaneously for the unknown quantities. Use substitution or any other method that you're familiar with. And then finally, you want to be checking your answers by substituting them into the original equations. Okay, let's talk about RC circuits, resistor capacitor circuits. So in the figure, we have a capacitor in series with a resistor, a battery, and a switch. And then the B portion is a plot of the charge of the capacitor versus time after the switch on the circuit is closed. So now we want to turn our attention to direct current circuits containing capacitors. In these circuits, the currents vary with time. So we're showing in the plot. Take a look at the series circuit in the figure. We can assume that the capacitor is initially uncharged with the switch open. After the switch is closed, the battery begins to charge the plates of the resistors and the charge passes through the resistor. As the capacitor is being charged, the circuit carries a changing current. The changing process continues until the capacitor is charged to its maximum equilibrium value. Here, epsilon is the maximum voltage across the capacitor. Once the capacitor is fully charged, the current in the circuit is 0. If we assume the capacitor is uncharged before the switch is closed, and if the switch is closed at t equals 0, the charge on the capacitor varies with time according to the equation shown here, where E is Euler's constant, the base of the natural logarithm. So we have a logarithmic relationship that we're starting to explore. The figure on the right is a graph of this equation. The charge is 0 at t equals 0 and approaches its maximum value Q as t approaches infinity. The voltage delta V across the capacitor at any time is obtained by dividing the charge by the capacitance. So if we take a closer look at this equation, in this model, it would take an infinite amount of time for the capacitor to become fully charged. The reason is mathematical. In obtaining that equation, charges are assumed to be infinitesimally small, but in reality, the smallest charge is that of an electron with a magnitude equals to 1.6 times 10 to the minus 16 coulombs. For all practical purpose, the capacitor is fully charged after a finite amount of time. The term RC is the equation is called the time constant tau. The time constant represents the time required for the charge to increase from 0 to 63.2% of its maximum equilibrium value. This means that in a period of time equal to one time constant, the charge on the capacitor increases from 0 to 0.632 Q. Let's see how this works by substituting T equals to tau into the equation. Note that a capacitor charges very slowly in a circuit with a long time constant and very rapidly in a circuit with a short time constant. After a time equals to 10 time constants, the capacitor is more than 99.99% charged. So in this figure, on the left, we have a charge capacitor connected to a resistor and a switch. And then on the right, we have a graph of the charge as the capacitors versus time after the switch is closed. Note, let's consider the circuit in the figure on the left, which consists of a capacitor with initial charge Q, a resistor, and a switch. Before the switch is closed, the potential difference across the charged capacitor is Q divided by C. Once the switch is closed, the charge begins to flow through the resistor from one capacitor plate to the other until the capacitor is fully discharged. If the switch is closed at t equals 0, the charge Q on the capacitor varies with time according to the equation shown here. The charge decreases exponentially with time, as you can see in the graph on the right. In the interval t equals tau equals to RC, the charge decreases from its initial value Q to 0.368 Q. In other words, in a time equal to one time constant, the capacitor loses 63.2% of its initial charge. Because delta V equals Q over C, the voltage across the capacitor also decreases exponentially with time according to the equation shown here, where epsilon is the initial voltage across the fully charged capacitor. So let's have a question to think about this. The circuit is closed in the figure below in a long time compared with the time constant of the circuit. What is the current be in the 2-volt resistor? And the answer is 2 amps. After the capacitor is fully charged, current flows only around the outer loop of the circuit. The path has a total resistance of 3 ohms, so the 6 volts battery will supply a current of 2 amps. So let's think of some practical applications of this. And so in this figure, we have a wiring diagram for a household circuit. The resistance R1, R2, and R3 represent appliances or other electrical devices that are operate at an applied voltage of 120 volts, typical of what you see in a home in the US. Let's talk about the household circuits. In a typical installation, the utility company distributes electric power to individual homes with a pair of wires or power lines. Electrical devices in a home are then connected in parallel to these lines as shown in the figure. The potential difference between the two wires is about 120 volts. Actually, the current and voltages are alternating currents and voltages, but for our discussion right now, we'll just assume that there are direct currents and voltages, and we'll get to that in a couple chapters. One of the wires is connected to ground, and the other wire, sometimes called the hot wire, is at a potential of 120 volts. A meter and a circuit breaker are connected in series with the wire entering the house, as indicated in the figure. So now we have a picture of a circuit breaker that uses a bimetallic strip for its operation. So in modern homes, circuit breakers are used instead of fuses when the current in a circuit exceeds some value, say 15 or 20 amps. The circuit breaker acts as a switch and opens the circuit. So the figure shows one design for a circuit breaker. Current passes through a bimetallic strip. Its top bends to the left when it gets too hot because of the excessive current. If the strip bends far enough to the left, it settles into a groove in the spring-loaded metal bar. Then the bar drops enough to open the circuit at the contact point. The bar also flips a switch that indicates that the circuit breaker is not operational. After the overload is removed, the switch can be flipped back on. Circuit breakers based on this design have the disadvantages that some time is required for the heating of the strip, so the circuit may not be open rapidly enough when it's overloaded. For this reason, many circuit breakers are now designed to use electromagnetics, which will be discussed in the next topic, the next lecture. When wiring, both the wire and circuit breaker are carefully selected to meet the current demands of a circuit. If the circuit is to carry a current as large as 30 amps, a heavy-duty wire and an appropriate circuit breaker must be used. Household circuits that are normally used to power lamps and small appliances often require only 20 amps. Each circuit has its own circuit breaker to accommodate its maximum safe load. So as an example, let's consider a circuit that powers a toaster, a microwave oven, and a heater. So think about that. Using the equation P equals I delta V, we can calculate the current carried by each appliance. The toaster rated at 1,000 watts draws a current of 8.33 amps. The microwave rated at 800 watts draws a current of 6.67 amps. And the heater rated at 1,300 watts draws a current of 10.8 amps. If these three appliances are operated simultaneously, they draw a current of 25.8 amps. That means that the circuit breaker should be able to handle at least this much current, or at least or else it'll be tripped. As an alternative, the toaster and microwave oven could operate on one 20 amp circuit with the heater on a separate 20 amp circuit. So here we have a figure, the connection for each of the openings in a 240 volt outlet. And in B, we have an outlet for the connection to a 120 volt supply. So many heavy duty appliances, for example, electric ranges and clothes dryers, require 240 volts to operate. The power company supplies this voltage by providing, in addition to a live wire that is 120 volts above ground potential, another wire also considered live that is 120 volts below ground potential. That means that the potential drop across the two wires is 120 volts. An appliance operating from a 240 volt line requires half the current of one operating from a 120 volt line. Consequently, smaller wires can be used on the higher voltage circuits without becoming overheated. So here in the figure, the hot or live wire at 120 volts always includes a circuit breaker for safety. And so in A, when the drill is operating with two wires, the normal current path is from hot wire through the motor connections and back to ground through the neutral wire. In B, shock can be prevented by a third wire running from the drill case to the ground. The wire colored represents electrical standards in the United States. The hot wire is black, the ground wire is green, and the neutral wire is white. You should be aware that a person can be electrocuted by touching a live wire while in contact with ground. This is often due to frayed insulation that exposes the conducting wire. The ground contact might be made by touching a water pipe or by standing on the ground with wet feet, because impure water is a good conductor. Obviously, such situations should be avoided at all costs. Electric shock can result in fatal burns or cause the muscles of vital organs, such as the heart, to malfunction. The design or damage to the body depends on the magnitude of the current, the length of the time it acts on the part of the body through which it passes. Currents of 5 milliamps or less can cause a sensation of shock, but ordinarily do little or no damage. If the current is larger than about 10 milliamps, the hand muscle contract and the person may be unable to let go of the wire. If a current of about 100 milliamps passes through the body for just a few seconds, it can be fatal. Such large currents paralyze the respiratory muscles. In some cases, currents of about 1 amp through the body produces serious, sometimes fatal burns. As an additional safety feature for consumers, electrical equipment manufacturers now use electrical cords that have a third wire called a case ground. To understand how this works, consider the drill being used in the figure. A two-wire device has only a wire called a hot connected to the high potential side of the input line, with the second wire is connected to the ground, 0 volts. If the high voltage wires come in contact with the case of the drill, as in the top figure, a short circuit occurs. In this undesirable circumstance, the pathway for the current is from the high voltage wire through the person holding the drill and to the earth, a pathway that can be fatal. Protection is provided by a third wire connected to the case of the drill, as shown in the lower figure. In this case, if a short occurs, the path of least resistance from the current is from high voltage wire through the case and back to the ground through the third wire. The resulting high current produced will blow a fuse or trip a circuit breaker before the consumer is injured. Special ground outlets called ground fault interrupters, GFIs, are now being used in kitchens, bathrooms, basements, and other hazardous areas of new homes. They are designed to protect people from electrical shock by sensing small currents, approximately 5 milliamps and greater, leaking to ground. When current above this level is detected, the device shuts off, that is, interrupts the current in less than a millisecond. So let's talk about conduction of electrical signals by neurons. And so a nice life science application. In the nervous system of animals, specialized cells called neurons form a complex network that receives, processes, and transmits information from one part of the body to another. The center of this network is located in the brain, which stores and analyzes information and transmits signals to different parts of the body. The nervous system is very complex with about 10 to the 10 interconnected neurons. The message transmitted by neurons are voltage pulses called action potentials. When a neuron receives a strong enough stimulus, it produces identical voltage pulses that are actively propagated along its structure. The stronger the stimulus, the more pulses are produced. When the pulses reach the end of the neuron, they activate either muscle cells or other neurons. There is a firing threshold for neurons. Action potential propagates along the neurons only if the stimulus is sufficiently strong. Neurons can be divided into three classes: sensory neurons, motor neurons, and interneurons. The sensory neurons receive stimulus from sensory organs that monitor the external and internal environment of the body. Depending on their specialized function, the sensory neurons convey messages about factors such as light, temperature, pressure, muscle tension, and odor to higher centers in the nervous center. The motor neurons carry messages that control muscle cells. These messages are based on the information provided by the sensory neurons and by the brain. The interneurons transmit information from one neuron to another. Each neuron consists of a cell body with attached input ends called dendrites and a long tail called the axon, which transmit signals away from the cell as shown in the figure on the left. The far end of the axon branches into nerve endings that transmit signals across small gaps to other neurons or to muscle cells. A simple sensory motor neuron circuit is shown in the figure on the right. A stimulus from a muscle produces nerve impulses that travels to the spine. Here, the signal is transmitted to a motor neuron, which is in turn sends impulses to control the muscle. So here is a picture of a stellate neuron from the human cortex. This figure shows an electron microscope image of the neurons in the brain. This is to give you an idea of what it looks like if you're not familiar with that. So here in the figure, we have an axon that is stimulated electrically. The left probe injects a short pulse of current, and the right probe measures the resulting action potential as a function of time. The axon, which is an extension of the neuron cell, conducts electrical impulses away from the cell body. Some axons are extremely long in humans. For example, the axons connecting the spine with the fingers and toes are more than 1 meter long. The neuron can transmit messages because the axon has special active electrical characteristics. The axon acts as an active source of energy like a battery, shown in an experimental setup to probe the electrical and chemical properties of an axon. Note that the outside of the axon is grounded, so all measured voltages are with respect to zero potential on the outside. The probes can be used to inject currents into the axon, measure the resulting action potential as a function of time at a fixed point, and sample the cell's chemical composition. Experiments like these are usually difficult to run because the diameter of most axons is very small. Even the largest axon in the human nervous system has a diameter of only about 20 times 10 to the minus 4 centimeters. The giant squid, on the other hand, has an axon with a diameter of about 0.5 millimeter, which is large enough for the conventional insertion of probes. Much of the information about signal transmission in the nervous system has come from experiments with the squid axon. In the aqueous environment of the body, salts and other molecules disassociate into positive and negative ions. As a result, the body fluids are relatively good conductors of electricity. The inside of the axon is filled with an ionic fluid that is separated from the surrounding body fluid by a thin membrane that is only about 5 nanometers to 10 nanometers thick. The resistiveness of the internal and external fluid are about the same, but their chemical compositions are substantially different. The external fluids is similar to seawater. Its ionic solutes are mostly positive sodium ions and negative chloride ions. Inside the axon, the positive ions are mostly potassium ions, and the negative ions are mostly large organic ions. Originally, the concentrations of sodium and potassium ions inside and outside the axons would be equalized by diffusion, but the axon is a living cell with an energy supply and can change the permeability of its membranes on a time scale of milliseconds. When the axon is not conducting an electric pulse, the axon membrane is highly permeable to potassium ions, slightly permeable to sodium ions, and impermeable to large organic ions. This means that although sodium ions cannot easily enter the axon, potassium ions can leave it. As the potassium ions leave the axon, they leave behind large negative organic ions, which cannot follow them through the membrane. As a result, a negative potential builds up inside the axon with respect to the outside. The final negative potential reached, which has been measured at about 270 millivolts, holds back the outflow of potassium ions, so at equilibrium, the concentration of ion remains. So some interesting details about neurons, if you haven't heard about that. So in this figure, we have in A, we have typical action potential as a function of time, and in B, the current in the axon membrane as a function of time. The mechanism for the production of an electric signal by the neuron is conceptually simple, but was experimentally difficult to sort out. When a neuron changes its resting potential because of an appropriate stimulus, the properties of its membrane change locally. As a result, there is a sudden flow of sodium ions into the cell that lasts for about 2 milliseconds. The flow produces the 130 millivolt peak in the action potential shown in the top figure. Immediately afterwards, there is an increase in the potassium ion flow out of the cell that restores the resting acting potential of 270 millivolts in an additional 3 milliseconds. Both the sodium and chloride ions flow have been measured by using radioactive sodium and chloride tracers. The nerve signals has been measured to travel along the axon at speeds from 15 meters per second to about 100 meters per second. This flow of charged particles or signal transmission in a nerve axon is unlike signal transmission in a metal wire. In an axon, charges move perpendicular to the direction of the travel of the nerve signal, and the signal moves much more slowly than a voltage pulse traveling along a metal wire. Even though the metal axon is a highly complex structure, and much of how the sodium and chloride ion channels operate and close is not understood, standard electric circuit concepts of current and capacitance can be used to analyze axons. The axon have equal and opposite charges separated by a thin dielectric membrane acting like a capacitor. Okay, we have a variety of assess to learn. I'm just going to quickly give the answer. And so these would be things that you can be reviewing on your own. So a battery is used to light two bulbs as shown. What happens to bulb B when bulb A is unscrewed from its socket? And the answer is the right bulb's brightness stays the same. Both bulbs have the same brightness. A battery is used to light two bulbs as shown. What happens to bulb B when bulb B is unscrewed from the socket? And the answer is bulb's B brightness stays the same. Consider the circuit below. Which resistor has the largest power consumption? And the answer is the 50 ohm resistor. Consider the circuit below. Which statement is correct? And the answer are statements number 1 and number 2. A battery is used to light a light bulb as shown. An identical battery is connected by closing switch S. What happens to the bulb? And the answer is the bulb brightness stays the same. A battery is used to switch a bulb as shown. An identical battery is connected by a closing switch S. What happens to the bulb? And the answer is the bulb goes out. Two batteries are used to light a bulb as shown. A third identical battery is connected by closing switch S. What happens to the bulb? And the bulb gets very slightly dimmer. So here's a circuit that will be just something for you to be thinking about as we move forward here. A battery and 5 identical bulbs are arranged as shown. What happens when the switch S is closed? And the answer is one of the bulbs does not turn on, the other 4 turn on with equal brightness. A battery and 5 bulbs are attached as shown, and when the switch is closed, 4 of the bulbs are lit. Which bulbs change when bulb B is unscrewed from the socket? And the answer is bulb B goes on, and bulbs A, D, and E stay on. A second bulb is connected to a battery as shown in figure A below. When a second bulb is connected as shown in figure B, what happened to the brightness of the original bulb? And the possible answers are 2, 3, and 4. A light bulb is connected to a battery as shown in figure A. When a second bulb is connected as shown in figure B, what happens to the brightness of the original bulb? And the possible answers are 2, 4, and 5. So I think we're seeing that there's more information that would be helpful to narrow that down. 2 light bulbs are connected to a wall outlet as shown below. Bulb number 1 is 100 watts. Bulb number 2 is 40 watts. Which statement is true? And the answer is the 40-watt bulb is brighter than the 100-watt bulb. Consider the circuit below. Switch S is closed at t equals 0. What is the voltage across the capacitor C just after the switch is closed? And the answer is 0. Consider the circuit below. Switch S is closed at t0. What is the current through the capacitor C just after the switch is closed? And the answer is 3 volts. Consider the circuit below. Switch S is closed at t equals 0. What is the voltage across the capacitor C long after the switch is closed? And the answer is 6 volts. Consider the following circuit. The capacitor is uncharged when the switch is closed at t equals 0. Which circuit is equivalent to the circuit for the instant immediately after the circuit is closed? And the answer is number 3. Consider the circuit below. Switch S is closed at t0. What is the voltage across the capacitor C just after the switch is closed? And the answer is 0. Consider the circuit below. Switch S is closed at t equals 0. What is the current through the capacitor C just after the switch is closed? And the answer is 9 volts. Consider the circuit below. The circuit S is closed at t equals 0. What is the voltage across the capacitor C after the switch is closed? And the answer is 4 volts. And finally, consider the following circuits. The battery and capacitors are identical and the switches have been closed for a very long time. At t equals 0, both switches are open. what pair of resistors dissipate more total energy? And the answer is both pairs of resistors dissipate the same amount of energy. Okay, that's it for giving some review questions. Now we'll just do a summary, a couple pages here. So first of all, Kirchhoff's rules in complex DC circuits. For complex circuits can be analyzed using Kirchhoff's rules. And so the first one is the sum of the currents entering any junction must equal the sum of the currents leaving that junction. And number two, the sum of the potential differences across all the elements around any closed loop must be zero. First rule, called the junction rule, is a statement of conservation of charge. The second rule, called the loop rule, is a statement of conservation of energy. Solving problems involving using these rules to generate as many equations as there are unknown currents. The equations can be solved simultaneously. And then for RC circuits, resistor capacitor circuits, in a simple RC circuit with a battery, a resistor, and a capacitor in series, a charge on the capacitor increases according to the equation shown. The term RC is called the time constant, tau. So tau equals RC. The time constant represents the time required for the charge to increase from 0 to 63.2% of its maximum equilibrium value. A simple RC circuit consists of a charged capacitor in series with a resistor discharged according to the third equation here. Problems can be solved by substituting values for Q, small q, capital Q, T, or tau into these equations. The voltage delta V across the capacitor at any time is obtained by dividing the charge by the capacitance. Using Kirchhoff's loop rule yields a potential difference across the resistor. Ohm's law applied to the resistor then gives the current. So in terms of sources of EMF, any device such as a battery or a generator that increases the electrical potential energy of charges in an electric circuit is called a source of EMF. Batteries convert chemical energies into electrical potential energy, and generators convert mechanical energy into electrical potential energy. The terminal voltage delta V of a battery is given by the equation shown, where epsilon is the EMF of the battery. I is the current and R is the internal resistance of the battery. Generally, the internal resistance is small enough to be neglected. For resistors in series, the equivalent resistance of a set of resistors connected in series is given by the equation shown. The current remains at a constant value as it passes through a series of resistors. The potential difference across any two resistors in series is different unless the resistors have the same resistance. For resistors in parallel, the equivalent resistance of a set of resistors connected in parallel is given here. The potential difference across any two parallel resistors is the same. The current in each resistor, however, will be different unless the two resistors are equal. And that's it for this chapter. Thank you very much.